Okay. Hello everyone. Because Dr. Lin cannot make it today, so I will be your supply teacher to give you a talk about bioimage analysis with FIJI and AI tools. So I'm Wei Chen Zhu from ICOB Image Co. and also belong to the EA BIAS, the East Asia Bioimaging Analysis Society. So today's PowerPoint will be provided freely for you. So you can download through this QR code and also the link. And this training material is CC by license. So that means you can use this for any purpose. Just mention who made this PowerPoint. Okay. So before getting started, let me introduce myself. So I was trained as a developmental biologist using Drosophila as a model system. So I took my PhD program in IMB just nearby. And I spent several years for postdoc training at Riken, Japan. And 4 years ago, I got the chance to come back to Taiwan and I applied for this job, the Korean Image Co facility job. So until now, so I stay for 4 years. So this is today's outline. So basically my talk will divide into 3 parts. So the part 1 include the basic terminology and also introduction to FIJI. So for most of you, this part is particularly important because not everyone use bioimage analysis workflow or writing code, but the part 1 is especially important for most of you, especially for publication. And then I will go into introduce part 2. So tell you what is bioimage analysis workflow using a more classical way. And the part 3, I was talking about the open source AI software in bioimage analysis. So what is image? This is a single channel or is a grayscale image. If you zoom in, you can see there's a lot of square shape. So one square shape we call picture element or pixels. Each pixel is corresponding to a pixel value. So you can see a pixel value inside in this square. So, but how those colors can be applied is due to a lookup table. So according to this lookup table, we assign certain color to those images. For example, white is assigned to 2.5, and this is gray and is assigned to this color, and the black is 0. So according to the lookup table, we can have appearance of image. So basically, there are 2 types of image can be found. One is RGB color image. For example, the pathology section picture taken by color camera. So those images are composed of red, green, and blue. So we have 3 channels combined together, and the color camera take those color image at once. And we also have another type, is a fluorescent microscope, or we can call it multiple channel grayscale image. So we take individual channel individually, and then we merge them together. So first is the RGB color. For example, this is H and DAB stain. It's very common staining. Maybe you see a lot on the paper. So this is taken by color camera, and then we can spray into red, green, and blue 3 channels. So only those 3 channels assembled together is a 4D color image. So this color image. But either one cannot represent a full information. Usually for this type of image, we need to use a special technique called color deconvolution to separate the special color, for example, the DAB staining or H staining. So the color 3 is the residue of those color, means not color 1, not color 2. So it's the residue. So for fluorescence image, we take multiple grayscale channel, for example, channel 1, and channel 2, and channel 3. And then we assign those grayscale to a certain color, certain lookup table. For example, channel 1, we assign to magenta. Channel 2, this should be mitochondria, we assign to the yellow, and channel 3 assigned to cyan. And then we merge them together. So we have 3 individual channels. So let's talk about more regarding the lookup table. Sorry. So this is one image taken by a camera. So the camera got some pixel value, and those pixel value will be interpreted to certain presentations through this lookup table. If we use grayscale lookup table, this looks gray. And if we apply to the cyan or blue, it looks blue. And this is a fire, and this is like rainbow color. So although the picture looks different, but their pixel value inside is the same. Okay, this is very important concept. Okay, you can apply different color, different lookup table, or different pseudo color, but the inside the pixel value should be the same. Then how can we address the brightness and contrast? Sometimes we have to address brightness and contrast for the presentation purpose. Sorry. So if you simply change the pixel value, that's a bad idea because you change your raw data. The safe way to increase the brightness is change lookup table. So we change the lookup table so the picture looks different. The contrast was enhanced, but the pixel value remains the same. So this is the most important concept I feel I need to tell you. So lookup table and pixel value. And you can choose many different lookup table or different colors. Traditionally, biologists like red, green, and blue. Because, for example, IFP looks like red. GLP is green, and DAB staining is blue. So we just use the same color like what we see. So classical or more conventional way, people use this RGB combination. But if you compare blue one, it's not clear as cyan or grayscale. So blue is not for visibility. And also red and green is not friendly to colorblind. So currently the image community try to let you have a concept. So there are some people are colorblind, so try to make your figure colorblind friendly. For example, if you have 3 colors, then use magenta, yellow, and cyan. This will be more friendly. But for the best presentation, you can separate into different grayscale image like this. And for the merge image, you can show the combined color format. This is very common, you can see on the paper. So the green and red. So people who had red blind or green blind, this simulation, what they see is the same. They see a yellow. They cannot distinguish there are 2 patterns. But if you simply change the red to the magenta, they can distinguish there are 2 patterns. So this is very important. So don't use red and greens together. Although you see a lot of paper use this kind of combination. Then let's talking about the bit dips. Maybe you took some computer or computer science at high school. So you should know what is bits. Bits is 0 or 1, right? So if one pixel or one image, the bit dips is 1 bit. So we can only have 2 values, either 0 or 1. So if you see the image, that would be black and white, only 2 difference. So if you have 2 bits, then you have 4 combination, 0, 0, 0, 1, 1, 0, and 1, 1. So there are 4 combinations. So you can have 4 different values. But the first value is 0, so the value will be 0 to 3. So you can have more detail. And if you have a bit format, 2 to 2 to the power of 8 is 256. But first is 0, so you have 0 to 255 value. So this is very common. You see the image, you can see if that is a bit, the pixel intensity will be distributed within 0 to 255. So, but if you want to quantify your signal intensity more precisely, then use higher bits. Dips is better. For example, 12, 14, or 16 bits. So you can have more details to record the difference of those intensity. But remember, the basic unit of computer for storage is byte. So 1 byte is 8 bit. So that means 8-bit image took 1 byte. But for 12, 14, or 16, they also require 2 bytes. So sometimes a computer cannot distinguish what is the real bit dips. For example, when you open an image, if they say 16 bits, you have to be careful to check your camera. Sometimes camera setting is just 12 bits. So the maximum value will be like 4,000, not 35,000. Okay. Okay. Then what is the pixel number, pixel size, and resolution? So first is the pixel number. So that means the total number of individual pixels to make up this image. For example, this one is 512 pixel by 512 pixel. And this one 16 pixel by 16. So sometimes, for example, camera or a phone, for example, they will say the resolution is, for example, 10,000 million pixel. But that means the pixel number is not really the real resolution. Okay, that means how many pixels they can store. And this cell has the physical size, for example, it's 64 micrometer. So if you divide these two values, you know 1 pixel is 0 to 0.125 micrometer per pixel. And if you use less, for example, 215 by 215, 256, and now each pixel is become bigger, so the pixel size is increased. Okay, 1 pixel represents a bigger area of this image. So this is pixel size. And what is resolution? So here the resolution especially refer to the optical resolution or resolution in microscope. So this is a property of image system. This means how small object can be distinguishable. Okay, so sometimes optical resolution need to be matched up with pixel number. For example, this is true field pixel number, and you see it's very blurred like this. If you have enough pixel number, then the cell become very clear like this. What is the best sampling? I mean, the best number that match to the optical resolution. That is a big issue. And you can learn more from those online video. It takes maybe more than 2 hours. Okay, so if you want to learn more, check those online resources. The image can be 2D or 3D. So in the 2D, 1 pixel is a flat. In 3D, it's like a cube. So we have X, Y, Z plane. In 3D, we call voxel. So for example, if you have experience to use confocal microscope, we will take a confocal Z stack. So we will have a different Z focal plane.
Your laser point did not show in the past.
Okay. It will tell me. So, like this. Okay. Okay. Thank you. Okay. So then we can have multiple channel image and with multiple time point. So this can be 3D plus different channel, different time. So we can have a 5D image like this. So if you have multiple channel, then for the fluorescence, usually you have N color means you have N channel. But if you take by color camera, no matter how many colors are represented, they only have one RGB combination, like one channel. Okay. So file format. So when you take an image, usually by commercial system, they have a raw file. For example, this is CZI, Leica is .diff, Olympus.oir, for example. So those raw file is most important file because it keep all the metadata. Metadata means the additional data that recording, for example, dimension, image type, bit depth, and microscope setting. So those metadata is very important for your publication. Sometimes paper may check your raw file. So always keep a raw file for your study. And there are also other image file. For example, TIFF files usually use for publication, but sometimes we can use for image analysis. But be careful, depends on the setting. TIFF file can be non-compression or lossless compression. This is fine. But sometimes in some special case, TIFF file can be lossy. For example, if you select a JPEG compression in a TIFF file, that may cause some data loss. Now we have other format, for example, OME TIFF. This is trying to standardize the metadata for microscopy. If you search on the web, sometimes people share the image with OME TIFF because they want to convert those raw files into a standard format. And the next generation file format will be OME ZAR. It's not so common nowadays, but it will more important because this kind of trunk file system, so it's very good for big data, especially if you have for example, 1 TB of image you want to display to others, then this will be very important. JPEG can be used for display or print, but not suitable for analysis. And JPEG basically don't use it because this will lose some data. Okay. Then let's talk about the ImageJ and FIJI. Maybe you know ImageJ and FIJI are quite similar, but actually they're a little bit different. So the original ImageJ was developed by NIH, and it has its own application for ImageJ, and then some people rewrite into ImageJ2, and ImageJ2 combined with many plugin. Then nowadays most of people use FIJI. So if you use ImageJ side ImageJ, if you use FIJI side FIJI, they are different. But when you open the FIJI, they say FIJI is just ImageJ. So sometimes people confuse, but yes, they are pretty similar. So you can see, we can say FIJI is a powerful version of ImageJ. So it's combined a lot of plugin inside of the FIJI. And you can download from this website. FIJI is very easy to use and it's free. One most important point for FIJI is updater, a FIJI updater. So if you go to FIJI and update, then you can manage your update site. So here, you can choose the plugin you need. You can just click or you can search, and then you can install those necessary plugins for your research. So here's a list. So you can check this list to find some useful plugin for you. And because if you have experience for FIJI, you know there are too many comments inside of the FIJI. Sometimes people forget how to find that comment. So there is a search bar here. So you can just key in some keyword and then you can find the particular comment and you can run directly. If you use ImageJ, there's a FIJI arrow, so you can use command finder to find your necessary function. Okay, so then how to open the data in FIJI? So usually we just drag and drop. So then we can open the image. So by doing so, you can open generic image format, for example, TIFF or PNG or JPEG. Sometimes you can open a folder. A folder contains a series of image. And you can also open ROI file. I will talk about this later, or image macro. And if you open a raw file, like CZI or LIB, then a format import option will be automatically pop up. So this is something like converter from the raw image to the generic format. So format importer, they have many options, but I just tell you the most important one. So usually I don't check those options at all, usually. And there is a color option. I will select composite, means every color are merged together. So this will show you a merge image at the beginning, and later you can decide which channel should be shown or should be disabled. And if your file is too big, here is a virtual stack. If you check this one, that means they only load in a particular, for example, particular time point at once, not loading all the data. So this can help you to process a very big image. Okay. This is FIJI user interface. If you open image, you can see here, there's a zooming factor. So you can use a plus or minus key to zoom out or zoom in your image. And here you can see the image size in physical size or in pixel. And here you know what is the channel you are select. For example, now its selection is on the magenta channel, the channel 1. So if you select channel 1, then if you go to any point of the image, it will show a pixel value of channel 1. If you want to measure the channel 2, you have to switch to channel 2. And the current position in the space, like for example, this is the position, the fourth Z state, or the certain time point shown here. Type. For raw image, it usually show 8-bit or 16-bit here. If that is RGB format, this will say RGB. So you can convert the different type through the image type, and for example, you can convert this to RGB for presentation purpose. It's very important in the FIJI, only one active window and only one active channel. So that means depends on which window or which figure you select, the measurement will only working on that on your selection. Okay, so I play a video for your reference. I open the image. You can see there are these slider bars, so you can check different these like this. And now it's the channel 1, so you can select to channel 2. And we can call the channel tours. Channel tours, and also we can call brightness and contrast control, and we can call histogram. Histogram is very useful to check the image quality. Okay. Then we can activate live, so you can see different channel, different stack distribution, and we can change the brightness and contrast. So notice here, so when we change brightness and contrast, only lookup table has been changed. So those statistic of image doesn't change at all. Okay, so histogram is very important. So when you check the image, you can use log view. So log view that you can see the fewer pixel distribution. And if you see a peak here at the 0 or at the maxima, that means your data is not recorded properly. So the data clip has been happened. So some data has been cut, either underexposed or overexposed. So the proper images should be, histogram should like this. So they have some background and there's no peak on the maxima value. And if you see there are some space in between the histogram, means some people do the rescaling of this histogram, means the intensity has been changed somehow. Okay, if you want to change the color, you can use the LUT, look up LUT button. So here, or you can go to image and lookup table. So here you can select different lookup table. For example, this red, and you can select magenta and channel 1, because we select channel 1. Channel 1 will be switched to magenta. Oh, by the way, my slide will be provided for you for download, so you don't have to take a picture anymore. Okay. And so this is useful lookup table. So most of people use, or traditionally people tend to use red, green, and blue. But for nowadays, colorblind friendly lookup table is preferred. If you have 3 colors, then magenta, yellow, and cyan, or even better, use grayscale. Those 3 colors has a variation we call magenta heart or yellow heart sign heart. This brighter version, usually paper not use this one, but for some paper or for image computation, this lookup table, this color looks really beautiful. So if you want to submit an image computation, you can consider those lookup table. And range indicator is very important to check whether your image is overexposed or underexposed. So there are two types, high-low. High-low is similar to Zeiss microscope system. So the zero part here actually is showing blue. And for the maxima value is shown in red. So if you change the lookup table to high-low, and if you see red means overexposed. And if you see the blue means underexposed. So the glow is used by Leica microscope. And it's a little bit, I'm not so familiar with this, but they usually use glow to indicate overexposed and green for under. And sometimes you can choose this kind of heat map like lookup table, like fire or green, fire, blue. And in the later half part of this talk, I will show you image segmentation. For image segmentation, we need this kind of lookup table. So for each value, we give a different color. So this helps us to distinguish the different label or different object. If you want to show those calibration bar or color scale, you can call a function calibration bar. So you can find this in Analyze Tools and Calibration Bar. So this function only works on single channel image. So you have to either split the channel or you have to duplicate the single channel to apply this function. And then you can, for example, if I apply this fire lookup table, then we can create a calibration bar. And remember, the brightness and contrast setting will affect the value here. So change the brightness contrast first and call the calibration bar later. So for image to compare, you need to image under the same condition, under the same parameter. And if you want to show data, you want to compare the intensity, you can adjust brightness and contrast, but those adjustments need to be the same. So if you want to apply the same display range or brightness and contrast, you can use this function. So there is a set function here, and you can key in a specific value for the minima display range or maxima display range, and you can propagate to all other two images. So this will apply the same setting to the all other image you open. And don't use auto function independently for each image. Some people use auto for individual image. What that means, so you will get different brightness and contrast adjustment for each individual sample. So sometimes it causes problem. Some people has been rejected due to this issue. Okay. And we can create a Z projection. So this is a Z stack, confocal Z stack. And we can make a Z projection to let this become like a single image. So there are you can find the image and stack and Z projection. So there are different methods to select. Most of the case we use max intensity to give you a max intensity projection. So this is most commonly used. So what is the maximum intensity projection? So suppose you have 4 layers for these decks. So max intensity only pick the maximum value, for example, 250 as a representation. So the other will be discarded. So if you use maximum intensity projection for example, colocalization analysis, you must be careful because if you see two signals are colocalized, maybe they are under the same Z stack, but you merge them. It looks like on the same position, but this may not be true. Okay, for signal quantification, I personally prefer use some slices. Some slices means we add all the value together, but not only take the maximum value in account. But remember, if you want to use some slices, you need to use the same number of slices. For example, some sample, one sample have 10 slices, another sample you also need 10 slices. If you use different, then you have a different base to compare. And I usually open the image in a composite mode. So it will show an image like a merged image, but you can also separate the channel. This is sometimes important because some function only appears in the single channel image. So you can duplicate this one, and then you can separate the channel, and you can take one of the channel to further image processing. And sometimes we need to convert the raw data into RGB format because RGB format is good for presentation. For example, if I want to put a figure on PowerPoint or on our publication, it needs to be RGB format. So analyze using the raw image format. But for publication or presentation, use RGB format. Okay. In many cases, for example, sometimes I saw a microscope company to demo a machine, and you go to a demo and take some picture, then the staff will export RGB image for you. But that is RGB image, not the raw data. But if you got the raw data, then you have to convert to RGB format by yourself for presentation purpose. Okay, so there are 3 ways to convert the raw data into RGB format. So you can from the image type and convert to RGB color, or you can save as PNG. So PNG is always RGB mode. So if you save as PNG, it will convert to RGB automatically. But you will lose the metadata. For example, the scale bar information will be lost. And you can also use image overlay and flatten. There's a hotkey, so you can have a very quick way to get the RGB image. So always use the original image for analysis and create a RGB copy for your image for display or presentation. So this is why you should use original. For example, now it's in channel 3. If I select one point, it will tell you this point value is 212. But if you select the same point under RGB format, what you see is just 3 colors. How many red, green, and blue are mixed together. This is just for presentation purpose, not for quantification. And then scale bar. Scale bar is important. So you can use analyze tools and scale bar, and this menu will be pop up. So usually I the scale bar in RGB format because usually scale bar only need for application or presentation. So remember to uncheck the overlay here, because if you check the overlay, this will create another layer. So this layer, scale bar will be another layer, and this layer cannot be visualized for other software. For example, PowerPoint or other image viewer cannot see this scale bar. So I usually uncheck scale bar is easier. So this will be write this part as a white image. So other software can recognize this is white, and then it's good for presentation. Otherwise, you need to flatten again. If this is another layer, then you can flatten those two layers into one image. If you put a scale bar and you see this scale bar is some how many pixels, so this means something wrong. The metadata must be lost. Okay, so you need to calibrate this one. You can go to image and properties and key in pixel size here. And the unit you can key in like a UM or micrometer or micron. So after this calibration, you can get a proper scale bar. So this phenomena usually happen when you open a export image from the, for example, Zeiss, Zen software. They can batch export a lot of RGB format, but when they export those image, the metadata is changed. The export image, the purpose is for print or for display. So they change those metadata. And when you open that kind of image, the scale bar or the unit will be pinched, or sometimes it's totally no unit here. So they only know how many pixels are shown. So make sure you have proper scale bar. If you open the raw data from the microscope, usually this is fine. But if you open the export or process data, you have to take care about this. And I would like to introduce a very useful tools called visualization tool set. In my image code, I always teach people to use this tool set. So you need to go to update and manage update side. You need to select those three plugins. And after you install this, you can find a visualization tool set here. And maybe I just play a video that show you. So usually we need to show the figure like channel 1, channel 2, and merge. When I was a student, I used PowerPoint. So I export individual RGB format, RGB image, and I assemble those three different channel image and merge image by PowerPoint. So this takes time. But if you know how to use visualization tool set, you can call the visualization tool set here. You can use preview macro, and then you can select all option dialog. Here you can select color or grayscale, and you can label the image here. And the label is the annotation of this figure. For example, JP or RP or DP or whatever your gene name is. So just several click, you got a very beautiful image for presentation. And you can add a scale bar here. And remember to uncheck overlay. Okay. So this image already converted to RGB. So this is already perfect for presentation. And you can do similar things on the stack image. So this stack image will take longer time for convert. But now you have different Z-stack with different channel and also merge. So you can save this as a video. That is very useful to show a different focal plane. So when you play with the feature image, it is important to keep raw data unchanged. So we usually duplicate another image for manipulation. So you can use image and duplicate, or Ctrl+Shift+D is hotkey to duplicate an image. So sometimes you need to only duplicate certain subset. You can also use make subset function. So you can, for example, you can, if this is 5 channel image, you can just duplicate 1, 2, 3, and 4. You can skip one of these. Each duplicate cannot skip in the middle. So if you use this function, it must be continuous. But the make subset allow to keep middle listed or middle time point, for example. Okay, gamma adjustment. Gamma adjustment is kind of a way to balance the bright part and the dim part. For example, this is original image. This is original lookup table. If we take a gamma, then the brightness and contrast is non-linearly adjusted. So the original dimmer part will become brighter, but bright part not change so much. So this can enhance the weak signal part, but not so much on the light part. So this can balance the light part and weak part. So this is nonlinear change of image. So you have to mention in the figure legend if you use gamma adjustment. So let me show you this one. So there is people here. And if I change the brightness and contrast here, you can see there is a ghost behind. And now the detail of this people is gone because it's too bright. So no matter how you adjust, you cannot balance those two. But sometimes, especially in neuron image, soma is extremely bright and dendrite is extremely weak. So use gamma adjustment is a very effective way to balance those two. So now I use a visualization toolset to adjust the gamma to certain value. So now I can balance the weak part and bright part. I can keep those two details at the same time without change the value. So now the changing is actually the pixel value, but if you apply multiple times, sometimes it's cause problem, so you have to reset. The point here is if you use these tools to address gamma tools, you need to do it perfectly. And if you want to retry, you have to reset your lookup table and do again. Okay, so this is a community developed checklist for publication and image analysis. So this published last year. So you can, for the publication image, you have to annotation, proper annotation for channels. For example, you need to put standard marker or sometimes scale bar. And you can adjust brightness and contrast for better visualization purpose, but it's better to report adjustment. And for the image, for compared to image, you need to use the same brightness and contrast adjustment, and don't use auto adjustment for individual one. Zoom channel is usually not very good for human eye sensitivity. So for better visibility, use grayscale. And if you have multiple images, think about the colorblind people. So the best way is separate into different grayscale. And if you have two color, red and green is not good. Use red, use green and magenta is better. So this is the minimal requirement. And if you can provide a scale bar, a calibration bar, or pixel intensity, that will be even better. And if you use a spatial lookup table, for example, this original one, this is spatial lookup table, or you change the gamma value for better visualization purpose, it's better to put those images side by side. So those checklists so far is now very strict for each journal, but I believe in the future they will take those checklists very seriously. Okay, so if you want to know more for the figure making, these are some related training materials, so you can click those for you to watch to learn more. I should speed up. Okay, let's talk about the region of interest. Do you know what is region of interest? Have you anyone heard about this? So region of interest means I want to, for example, I want to measure this part. I want to draw or I want to put the annotation of this cell. So there are many of region of interest tools here. You can use rectangular or you can use circles. So there are some hidden function here. So for example, rectangular, and you can use right click or double click to change or to check those hidden menu. So there is also rotated rectangular, or you can use different tools. For example, different line or arrowhead. So region of interest, just simply you select a region you want to measure. Okay, so you can draw a rectangular like this, or you can draw a circular, or you can hold in a shift. So now you can have a composite region of interest, so they can measure those two places simultaneously. And then you can merge them together by holding shift and with some joy. And you can use ALT. If you use ALT, you can subtract part of them. And you can move the region of interest by click inside, and then you can move this around. If you want to unselect or delete, you just you can use this hotkey, Control Shift and A, and it will unselect. And if you make some selection on one figure and you want to transfer this selection to another figure, you can use Control and Shift and E. So this will transfer this selection to another image. So let's show you a tool here. This is brush selection brush tool. So selection brush tool, you can select a size of brush and you can make an annotation or you can make a selection for your region. So this is menu selection. And then you can add a T. T means add to ROI manager. So those selection will be saved in the ROI list here. Okay, so now you have two region of interest. Or you can use another magical wand. So this can allow you to select part of the image by a certain threshold. I cannot make it faster, so after you do some selection, and then here is a measure function, and you can click measure. You can get the measurement of those two area. So region or ROI manager, so if you have an ROI list here, you can save those ROI as an individual file. So if you select a single ROI, you can save as a .roi file. And if you select multiple, or you just deselect, deselect means I want to save all of them. Then it will save as a .zip file for the whole ROI. Measurements. If I click measurements, I can measure something here. What you want to measure will depend on the set measurements function. So you can go to analyze set measurements and select the necessary item you need. For example, the area and min and max gray value, for example. Gray value means the pixel intensity. Or you can use shape description, for example. And here is a very important display label. If you check the display label, then your measurement result will show these measurements come from which file and which channel, or which z-axis, or which time point. Okay, so this will be very important. And those measurements only show category and also the value here. There's no unit. So for area or length, the unit will be determined by the unit in the image properties. So you can check image properties. So this measurement, if the image properties show the unit is micrometer, then here will area unit will be micrometer square. Then you can use the plot profile. So this is a line ROI. So you can draw a line and use Control and K. And you can plot the intensity profile along this line. You can also double click and change the different size of the line. So you can include more area for the measurement. If you want to measure multiple color, you can use the visualization tool set. There, inside of this tool set, you can select here, and there is a multiple channel plot tools. Then you can plot for multiple channels. Okay, so The part one has been finished. Maybe we take a rest for 5 minutes. Okay, let's continue for the second part. Second part, I'm going to talk about the bioimage analysis workflow. So bioimage analysis is trying to extract some numbers from the image and convert those numbers to the knowledge. So usually bioimage analysis also means we want to understand, quantifying a microscope, medical or any other category image data. So bioimage analysis ideally or supposed to be quantitative and objective. Objective means no matter who did the measurements, the result should be the same. So the menu selection basically is a bad idea. And reliable, you should do some validate to know what is the measurement you are doing. And you can repeat the measurement several times, and each time you get the same result. So it should be repeatable. And reproducible means if you provide the image analysis workflow to other people can reproduce your image analysis result. So for this, the documentation is very important. And replicability means other people can do the same analysis, potentially on the other data, they can get the same trends. So this is very important concept for the bioimage analysis. So usually, this is a typical workflow. The goal is to quantify the observation and conclude those measurements with the numbers. So this is a raw image, and usually we do some image processing, make it clear or remove the noise, and we do a segmentation. So for segmentation, we can use classical image processing, or we can use AI. So during the segmentation, each cell will be labeled with different ID, and based on those ID, we can perform a further measurements. And then we can plot the different measurements. We can do some data visualization, for example. So there are some key terminology here. So this is the raw image, or we can say this is the intensity image. We can use thresholding. We can say signal above some threshold is can consider as a foreground, and the others consider as a background. So this is thresholding. So we can use thresholding method to convert the raw image to a mask or a binary mask. So the binary mask can be further processed to become individual label. So this process called connected component label. Or in FIJI or ImageJ, we can convert the mask to the ROI, or from the label to the ROI. So the region of interest. So based on this ROI, we can do some measurements. So nowadays, the AI-based segmentation tools can allow you skip those steps. So you can, from the raw image, you got the label, and in the FIJI, we can rely on this label to convert into ROI, and we can have measurements. So what is thresholding? If you open the image, it should be a single channel image. You can use image address and threshold, or Control then T, and you can find this threshold menu. So most of people, for the first time, they may manually select different thresholding. But the better way is try to avoid menu addressing if possible. What you should do is you need to select auto thresholding algorithm here. there are many different algorithms. You just need to select one that fit to your data set. And you need to use the same algorithm for all the image. So that makes your result can be reproducible. So this image, and so algorithm may find a threshold to divide the image into background and foreground. So then we can get the threshold result, the mask. So those thresholding has a paper. So we need to cite those paper. For example, the famous thresholding method, OTS, is published a long time ago. If you use certain thresholding, you should also cite. So you can say we segment the cell nuclei in the image using all the thresholding method and cite paper implemented in the FIJI. So this is important. Many people just don't cite. Yeah, but the cite those is important. And sometimes image is not perfect. So for example, maybe not perfect focus or some blur, or we have some background due to difference of the issue, dirt or whatever. And we also have some noise. Camera has this noise. So together, those effect, you got the image. This is a real image like this. So if you use this kind of not so good image, and for the segmentation, you got a bad result. So for those bad segmentation, the computer will recognize as a thousands of tiny objects, not a big nucleus. They just recognize thousands of objects. But you can process them using some image filtering, and you can get a better segmentation result. So image filtering, sometimes not just the noise, but for example, the nuclei itself. If we keep too much detail here, it's actually not good for thresholding. So sometimes we make it a little bit blurred. And those blurring can help you get the proper thresholding. And you can convert this selection to the original image. So the measurement should be on the original one, but not the blurred image. And there are many of filters. So linear filter. So linear filter just a pixel that will be multiplied a kernel. For example, this is a min filter kernel. So each of pixel will calculate the, let's say, this will calculate like this. You can see this animation. So for each pixel, it will calculate the surrounding 9 pixels and get the mean value, and replace the same position with a new mean value here. So this is so-called mean filters. And sometimes we use nonlinear filter, for example, the median filter. So for this pixel and its surrounding total 9 pixels, we put them in a rank like this, and we can pick the median value as a new value of this pixel. This is a median filter. Or you can put a max or mean filter. So this is kind of non-linear filter. So filter kernel. So the example here is always 3 by 3, but sometimes you can have different size or different shape of the kernel. So it depends on the algorithm you use. So if you use a smaller one, the effect may not so strong. So sometimes you still cannot get proper threshold result. You can optimize those parameters to find the best parameter for you to get a better thresholding. And mean filter and median filter, actually, I rarely use mean filter, but the median filter is extremely useful. For example, if an image with a lot of noise, we call salt and pepper noise. So it means some noise are underexposed or overexposed. So because those noise are outliner, so it will be removed by the median filter because median filter only pick the median value. But for mean filter, they will take an average. So those noise will be remain after you treat with the mean filter. But median filter, excellent. You can remove all of this noise. And so sometimes we also use Gaussian filter, Gaussian blur. But median filter is even better for the edge preserving. So if you want to keep your cell shape, a median filter is better choice. And nowadays, there are some deep learning methods to try to improve the signal to noise ratio of your image, try to improve the image quality. But it takes longer time for computing. So most of the simple case, you can try either Gaussian blur filter or median filter. And in addition to noise, there's also another common problem is the background. For example, if we want to segment those dot panta, those panta, but here the background is high. So then we apply the thresholding, we will get a large area of those high background, but not those panta inside. So then we have to subtract the background. So there are a lot of ways to remove the background. In ImageJ, you can find a command called subtract background. It's based on the rolling ball algorithm. Or some people use divide an image by Gaussian blur image. Or my favorite is use difference of Gaussian filter. I don't explain the too many detail here, but basically you have different ways to remove the background. After you remove the background, then you can get the proper thresholding to isolate those panta. And then we can refine those masks by morphological operation. So suppose this is a mask, we can make those masks smaller. We call erosion. Okay, we can make it bigger, direction. So if we combine erosion and direction, this is called opening. Okay, opening can remove some smaller part. For example, smaller dots. We don't want to keep them. And sometimes we want to make it connected. So those, I think this should be connected. So we can use direction and erosion. So, or we call closing. There are also other like outline, fill hole, or skeleton. So there are many ways to deal with those masks. So anyway, so suppose this is a nuclei, we do some processing, either remove the background or noise, and we can do a thresholding. So sometimes even we do the pre-processing, this result is not perfect, then we can refine this mask. For example, fill hole, or we can apply water sheet to try to separate those capturing object. Okay, and we can have, sometimes we can have different masks. For example, we can have a wholesale mask. That's come from the thresholding of this green channel, or we can have a thresholding from the nuclei. And now we have two different shapes, and we can use the image calculator. For example, we can use A mask, subtract B, so you got the cytosol mask. Or you can do some other patient things like this. So image calculator is kind of useful when you want to do some spatial area or spatial localization processing. Oh, wait a minute. I need the power supply here. Okay, sorry for technical problem. And so after we have a perfect mask, we can perform a kinetic component analysis. So left-hand side is a mask. So we can fill a value for the nearby pixel of the void graph, and like this. Then now we can distinguish there are three objects, 1, 2, and 3, and the background will be filling with 0. So the maximum value here of this maximum value of this image also represent how many objects in this image.
Share with the online.
Oh, absolutely. Oh, wait. Okay. Thank you for your notice. And so kinetic component labeling, after this processing, we can have a different number of objects, different ID. And there are two different algorithms. So in ImageJ, we use A connectivity. So for example, this pink one is considered as one object because this direction also considered as a connected. But if you for some other software is used four-way connected. So this way, this direction 45 degree is not considered as connected component. So if you apply different algorithm, you may get a different result. But in ImageJ, it's mainly used a connectivity. So just for your reference. And you can expand this idea from 2D to 3D. So A connectivity in 3D is 26 connectivity. 4 connectivity in 3D is 6 connectivity. Okay, and in FIJI, we all usually use a function called analyze particle. If you have a mask image, then you can do analyze particle here. And so here, what I usually select is I select add to manager, means I add those segmentation to the ROI list here. And you can show those images as a count mask. Count mask is the label image. Okay, so by doing so, you can get ROI list. You can get the label image here. So let me show you an example. This is a very classical image analysis workflow in FIJI. So this is an example file. And I usually duplicate another image. And I can apply some filters, either Gaussian blur or medium filter. In this case, I apply medium filters. So medium filters can makes the segmentation result better, and I apply threshold. Now it's converted into a mask. So this mask may not perfect, so I want to do some mask refinement. For example, I want to spray the touching object by watershed, but before that, it's better to duplicate another mask. And then we can easily to compare the difference. So I can apply the watershed. So now the connected objects are sprayed. Then we can apply the analyze vertical. And here you can select a certain size or certain circularity for filter. And select the necessary item. So exclude the label on edge means, so those mask on the edge has been cut. I don't want to keep them because it's not complete cell. So then I can get the row list here and summary here, how many cell and the row list. So once I have the row list, I can apply this row to the original image for the measurement. And click measurements. Now I have individual cell area, mean, and integrate density, for example. So here it depends on the set measurements setup. You can have as many as the features you want to measure. So this is the label image. So now it's grayscale, so look like this. But if you convert into grass beyond dark, so this is best lookup table for the label image. Then you can see this beautiful representation. So this is a classical way of image analysis workflow. Then how can you describe this image analysis workflow? Maybe you saw this sentence on paper many times. Image were analyzed by image J. How can you reproduce image as result from that paper? You cannot reproduce, right? So we have to describe the image analysis workflow. But before that, I want to explain what is the collection and what is component. So collection is a software platform. For example, ImageJ, FIJI, or FIJI, for example. I will explain this later. So, but anyway, some software contains hundreds of functions, hundreds of plugins. And inside this collection, we have many components. For example, median filter is one component. Thresholding is one component, watershed is one component, and light particle is one component. So I take some of the component into a workflow like this. Then I can describe this workflow. So the best way is write ImageJ macro. So ImageJ macro is a great documentation to your image analysis workflow. So here, this is a workflow written by my friend. We can just run, and we got the same result. So every time you run this code, you get the same result, the same measurements. So this is very important for the result reproducibility. But the ImageJ macro sometimes is a little bit hard for biologists. But there is a simple way you can, oh, sorry, here I put this in the wrong location. So there is a plugin function, and you can find macro and recall. there is a recorder. So in that recorder, you can do anything you want, and the recorder will record every step you do. And then you can just modify that record script, and that's a kind of simple image analysis workflow. Or in the script editor, you can go to File, New, and Script. So there are some templates here. You can learn from those templates. And in this script editor, there is a function called auto code completion. So you just key in some keywords, and the rest of them will be complete automatically. And you can also ask ChatGPT for help. But don't just give a ChatGPT for image and tell him, please analyze for something, because every time you got different result. But you can ask ChatGPT to generate some image analysis code. After you got this code, every time you run this code, you got the same result. Okay? And then there is a cheat sheet, which I will introduce later. So writing an image macro is kind of fun, so enjoy debugging. You can download cheat sheet here. So it's kind of simplify menu. I think I don't have time to explain too many details here, but in cheat sheet here, because in ImageJ, we only have one active Windows, and we have only one active channels like this. So sometimes we need to select, for example, certain channel. We need to select certain channel, certain frame, or certain slices. So there are some necessary commands are listed in this cheat sheet. So you can print this cheat sheet and you can just try to play with it. And there are many other great learning resources online. So Dr. Robert Haas provides a very comprehensive bioimage analysis lecture online. So this is one. So this is his playlist and complete slide and cheat sheet. So you can start from here. And if you want to learn more, you can also refer to other image codes training material. And for EA BIOS, our Image Analysis Society in Taiwan and Japan, we also hold our training event. So there's a recording and training material online. So the recording is speak in Chinese. So if you want to learn in Chinese, maybe easier for you, you can check this one. Okay, so I'm a biologist. So I know coding is a bit difficult for people like me. So then here I want to introduce a plugin called Glitch. I just play this video and let you know what is Glitch doing. So Glitch can allow you process those images interactively. So we can simply just use right click and pop out a menu and select next step. And those steps are suggested by the experts. So for example, there was the first line will suggest the noise, and the second line will suggest for example, background removal. And the next step will be thresholding, for example. So they have some design for this workflow. And each menu or each image are actually connected together. You can see this line. And we can try to change the parameter in one of these workflow. And the result will be also simultaneously calculated. So this so-called interactive workflow. So you can try to change different places, change parameter, change algorithm, and see how the result look like. And finally, you can generate a script here. Just simple click, and then can generate script or visualization. Also, this is kind of data visualization for the guys circularity maybe. And then you can generate the script. So just by clicking, so you can cut the script. You can reproduce your analyzed result every time. And this can generate human readable protocol. So this human readable protocol can help you to write the method session. Just looking here, you know how to write in the method session. Okay. Glitch need additional installation. It requires install a lot. So go to help, manage update site, and you need to select all of those plugins. And then you can try to play with the glitch. I don't have too much time to introduce glitch, but there is a YouTube playlist by Dr. Rob Haas. You can check here. Or if you want to learn in Chinese, our eBios training event, I give a lecture for glitch for 1 hour. So you can try to see this one if you are interested in this interactive image analysis workflow. Okay, let's go to the part 3, the AI in image analysis. So AI is artificial intelligence. I think I don't need to talk much about this. And for Bioimage part, we have different tools. For example, machine learning tools. The first one may be the Vika Tremble plugin, and later LabKit, or one of today's topic, Elastic. So this allows to just simple join some label and let's say this is cell 1 and one type of cell and another is type of background or something, and then you just did some annotation and train that the computer will help you to distinguish other image. And deep learning tools, StarDist and CellPulse, or segment anything model. So today I'm going to introduce StarDist and CellPulse, particularly useful for cell biologists. And generative AI, for example, ChatGPT. So I am not going to talk about this today, but the key point is if you use AI to analyze something, keep in mind, you can ask them generate a code for you, but not ask them in analyze directly. But after you have generated a code, you can reproduce the analyzed workflow every time. It's a key point. Okay, so those 3 tools, Elastic, StarDist, and CellPulse, can help you on the segmentation step. So previously, I told you a lot regarding the image, the noise, background removal, and mask thresholding and kinetic component labeling. But in those tools, they can instantly give you a good segmentation result like this. And for data visualization or classify different cell into different cartridge, Elastic also is a very good tool to distinguish different cartridge of cell. Okay, so there are some basic terminology. Instant segmentation. So this is something like label image, right? So you know there are many cells, for example, or many cells, many nuclei, or many dots. So for each cell has its individual ID. So this is instant segmentation. Or you can have a semantic segmentation. That means we want to separate those things into different classes. For example, cell and background, or large cell and smaller cell, or different brain area. So this is so-called semantic segmentation. So for AI, it's usually training by humans. So training needs some annotation, or some people say ground truth. So I prefer to say annotation because ground truth may not be really true. It has some bias. Okay, so for instant segmentation, you need some people to do annotation on those cells. It's called sparse instant annotation. And based on those annotation, we can train the computer to learn how to make instant segmentation. For semantic segmentation, or we can say pixel classification, we need like a sparse semantic annotation. For example, we draw some lines to, for example, say here is a background, here is a foreground. And according to your annotation, the computer can learn how to distinguish those two. So let's start from the Elastic. Elastic, you can download from this website, and it has a Nature Math paper. So it's very simple. So I just draw several lines. One yellow is background, blue is foreground, and the software will instantly know and give some prediction. If you don't satisfy, you can further refine your training data set. So tips for annotation. Use smaller brush like this, because use bigger won't give you additional information. So this is good. And if you sometimes you see people do annotation like this, but this is waste some computer power. Okay, so make sure you make a clear annotation. For example, this is state, because in the boundary, the computer may confuse which is foreground, which is background, because they are too close together. And most of the time, you don't need to annotate too much. Sometimes, if you annotate too much, the computer also confuses. So let's play a demo here. So from the pixel classification, so we need to create a name. So I create a demo for pixel classification, then I can add some image here. So we can add image, example, up. You can add more image for training. But now I just select one of them. And next is select the features. So there are many features you can select. If you don't know which feature you need to select, you can select all, but it takes longer time for computing. Okay, so here is the different feature or different filter image. So the raw image has been processed through different filters. And based on your annotation and its relationship to those filter image, a prediction can be made. So then I can draw our background, and I can draw foreground. You can have multiple classes. So now I have only 2 classes, but you can have 3 or 4. So now just background and foreground, but you can have more. So then you can live update, and you can see the segmentation. So this part is not perfect, so I want to refine. So I add a new annotation here. And now the result looks perfect. So this is the basic usage of Elastic. Okay, and Elastic also allow you to do object classification. So this need some instant segmentation image and over probability image. And with some annotation, then we can separate the cell into 2 different classes. Okay, so let's show here. So here is different features like histogram or the shape. So those images are already segmented in previously. So the input image also is already include those segmentation or the label image. And now the selection is just to say, hey, this cell is the label 1, belong to class 1, or this cell is belong to class 2. And based on the selection features, computer can try to understand what's the difference between those cells, and they can make other cells for prediction and make a classification. So Elastic itself is independent software, and for the data exported by Elastic is a format called HDF file. If you want to load HDF file into the FIJI, you need to install Elastic plugin. So again, you can go to update and manage update site and find Elastic and apply. After install this, you can load the Elastic file. So you can go import HDF file here. Or your further analysis of this. Okay. Next is StarDisk. StarDisk is very good to segment the nuclei or similar shape object. So this can only recognize a star convex shape like this, but this is non-star convex. So StarDisk cannot segment those kind of cell or nuclei properly. Only star convex shape is okay. And another advantage of StarDisk is StarDisk allow you to segment cells that share some overlap region. So for some very dense cell area, StarDisk is one of the best to segment those cells, even they have some overlap. For example, some brain region, they have a very dense cell, but StarDisk can allow you to segment those very dense or overlap cells. So StarDisk itself is trained by many fluorescence nuclear data, either in single channel fluorescence data or in HE-STAN. So basically, you can segment fluorescence image, or you can segment HE-STAN histology data. Okay, so if you want to install StarDisk in FIJI, you can use update and major update site. You need to install CSV deep and also StarDisk. Then you can call StarDisk 2D, because in FIJI only allow 2D segmentation here. If you want to use 3D, you have to use Python. So Python, static Python support 3D. So here you can simply find static 2D here, or you can search and then start this menu will pop up, and you can just click here, and you got those results. So it's allowed you output either raw list or label image or both. So you can have either you can have both for your process. The limitation of static is only support the cell number within the 16-bit limit. So that is 65535. So if your cell is larger than this number, you need to use Python. So start this setting here. You can select different model. So you can select the fluorescent nuclei, or you can select actually stem model. So you can also download a model from other pre-trained model from the internet. So you can look here. So here, the pre-processing setup here, percentile low and percentile high means we want to skip some very low signal, and we also want to skip some very high signal. So this kind of correction of underexposed and overexposed. So we usually check normalized data and also correction of low and high value. And here, probability setting here, if you give a high setting here, you get less cell, less segmentation. If you feel the cell is too less, you can reduce this probability or score. And here is the overlap threshold. If it's 0.3, it allows 30% overlap. If you don't want to allow overlap, just use 0. You can download other model from Bioimage Model Zoo. So other scientists already trained different of cell type, including plant cell or mice or whatever. Those models can be reused, can be downloaded from internet. Not only static, but also other AI software. So you can download their AI model, which are models that similar to your data set, and then you can reuse their model here. In case of the pre-trained model is not good for you, you can find better model that fit to your data. So here is another learning material from the EMBL. You can learn how to use image model loop properly here. So here is a demo. So here is the nuclei, fluorescent nuclei demo. So I can call start this 2D. And because it's fluorescent cell, I select fluorescent model. And initially you can use optimized setting and just click OK, and then you got the segment result in label and also in ROI, the raw list. So the other is like a histological section. So you need to use another model. So here, HE stem, for example. And I try. Okay. So this time, I think the segmentation is not perfect. So you can refine your parameter, especially the probability. To lower the probability, then you can have even better segmentation result. Okay, I think the third one is similar. Okay. The third one still use the same. And here you can see there are some overlap here. So this is one of the advantage for Starbase is allow the label overlapping. So far, this is the only one tools I know allow overlap. All other tools do not allow this overlapping. Okay, so if you use Starbase, you need to sign those ribbons. Then we go to the cell post. So cell post is maybe the most useful for biologists. So the training of cell post initially relies on difference of cell type, including cell culture or even plant cell or something even I don't know what is that. So all those different type of image can be segmented properly by cell post. So cell post, the first version of cell post, they aim to develop a generalist, the one algorithm for all type of image. But later they find that is not a very good idea because some variation may appear. So sometimes different cell, only one algorithm is not very good way to distinguish the different type. So then they have a cell post 2. Cell post 2 allow you retrain the model. So if you don't satisfy the prediction model, you can retrain by yourself based on their models. You can refine their model. Okay. Then later, cell post 3. Cell post 3 include image AI denoise or AI say AI clearly. So it's improved the image quality. So you can, by doing so, you can have a better segment result. So let's demo for Cellpose 3. Cellpose 3 is a Python-based tool, so you need to learn how to install on Python. But here I just want to show very brief. Once you install this, I can activate a Python environment, and then I can call Cellpose. Cellpose is I'll say it has a GUI user interface. Then you can load an image into this interface. Okay, so here just change the countries. Then the important thing is the diameter. You need to give the software know what is the diameter of your cells or your object. So like this, you need to match to your sample. Or you can use calibrate. Calibrate means the software will automatically detect the size or diameter of the cell. Okay, now it's detect as 77. And then I can run a Cellpose model. You can also select different model here. So usually the Cyto 3 or Cyto 2 is very good. So here I just run Cyto 3. And then I got the segmentation for those cells. This is bright field or maybe DIC image. So this is very hard to get the proper segment under a traditional way. So if you have bright field or you have DIC image or even phase contrast image, Cellpose is an excellent tool. Then you can save that label image here and import into the FIJI. And then you can change the lookup table. Then you can convert this label to ROI. There are several tools can be used. You can use BIOP tools. You can label to ROI image. Or another, later I found that this tools is better. So by Box or 3D Box, there's labels to 2D ROI manager. So after you convert the label to ROI, and you can measure on the original image. Okay. So here, just click measure, and you got the every measurement for every cell. Okay, then later, Meta AI, the company of Facebook, they developed a model called segment anything model. So segment anything model was trained mostly by natural image or let's say artificial image, many different photos. Okay, but they also include some cell image for the training. So there's a plugin called SimJ, but I think I don't have time to introduce today. But what I want to say is CellPose, the latest version of CellPose also integrate the same segment anything model. So they combine together. So they provide interface online. You can try to segment the image without install Python or CellPose locally. So just go to this website and you can upload your image and you can run CellPose Sim just online. If you want to install CellPose, you can go to CellPose GitHub and follow their instruction. It's a little bit hard for beginners. So if you want to learn how to install, you can check my previous video here, explaining in Chinese. So the current, if you follow the current instruction, the version will be 4.04. It's the CellPose Sim, but so far there are some bugs. I heard from the image forum. So if you want to specify older one, you can use this command to specify the older version. Then I think so far it is more stable. But if you want to try the latest one, you can go to the online web. So here you can just segment online.
So if you want to try CellPose, then should we update the CUDA version of the CellPose 3 we already installed?
CUDA?
Yeah, because
so there are two versions. So if you just follow here, it's a CPU version. So basic installation is just for CPU. If you want to GPU acceleration, it's need additional step. So you can check this video. I introduced how to install CUDA and related PyTorch.
My question is about, I already installed the CellPose 3 and with the CUDA version. So if we want to try CellPose, then should we update the CUDA version?
My suggestion will be you create a new environment to install CellPose, a new environment. So you separate different version. So you can keep the old version and you can try new version under different Conda environment. Okay, so if you use CellPose Sim, you need sign CellPose Sim paper. If you use CellPose 1, 2, 3, you need sign related paper. Okay, so all those tools can generate label image, for example. So then you can convert those label image to the ROI by a very useful plugin called Biobox or 3D Box. So you can just here. This function, it can convert the label to 2D manager. It's also supports 3D, so there's another function called label to 3D drawing managers if you want to try 3D. But yeah. Okay, so that's summary. Today you learn how to segment the image. From the raw image, we do some pre-processing and we got a mask here. So mask just yes or no. Okay, so is cell or not. So foreground and background. And we can use analyze particle to convert the mask into the array list. And in the array list, you can measure the different cell. Or you can convert into label image if you select count mask here. So this step is kinetic component labeling. So now I also tell you there's a plugin, Voxel 3D Box can convert labels to ROI. Then this is important because many AI tools, they only generate label image. So you have to convert those label image to the array list, and then you can measure your cell or whatever. Okay, so let's go back to here. In bioimage analysis workflow, sometimes it's come from different software, or different collection. For example, you can do segmentation by cell pose, and you can use, for example, glitch for exclude label on edge, and then I use Voxel 3D tools to convert the final label to array list, and then I can measure an original image. So I combine many different components to assemble into a workflow. This is how what you should describe in your paper. Okay, so again, this is the checklist. If you use the established workflow, you can just cite that workflow and with some key setting, or sometimes we have manual employee. And so this is a minimal requirement. So you need to know what workflow you use, some key setting and example data, exact version, or manually if you have. If you develop a new workflow, you have to cite the necessary components and platform, and also similar analyze sequence, key setting, data and code, or manually, and exact version are necessary. Okay, so it's also important if you ask someone, for example, the image code facility for image analysis. If you got a suggestion from them, remember to give them acknowledgement. If you ask them to write the image workflow code for you, you should include that capacity member as a co-authorship. So this is a guideline. Now it's worldwide accepted. Okay. Then previously we hold our local East Asia Bioimage Analysis Society training event. I don't know, maybe you saw this poster somewhere. Okay, so we hold this course in NTU, and we have 7 classes. And now all the recording are provided on this website. You can go to our EFL's website here, and you can find the resources. There's other resources also, but this is our own training material. Okay, so then if you are interested in bioimage analysis, so consider to join the GLOBIAS, Global Bioimage Analysis Society. And this is website, and you can find some webinar here, and you can find their YouTube for the previous webinar. So in the end of October, there will be a conference, Korea's Bioimage Analysis conference, and also training school here. So if you want to learn more from the experts, you can attend this conference and join the training school. So the registration deadline is 15th of June. 15th of June. Okay, so you still have time to consider. So this will be holding Kobe, Japan, Recon Media, the workplace when I doing a poster. Okay, so this is the final slide. This document, or I should say, I was highly inspired by Dr. Rob Haas. So I learned almost everything from him at the beginning. And of course, later I learned many other things from other people's. But he's my initial mentor for bioimage analysis. And later, our local image core facility, including NTU Image Core, IBC, IPMB, ICOB, and also expert from Recon, we together to assemble his BIOS, EA BIOS. And so we regularly update the latest training material on that website. So please visit our website frequently if you are interested to learn those things, and also copy us. Okay, thank you. Is there any questions? Is today's course too hard for you or too basically? Okay, if no more question, okay, thank you everyone for joining. If you have a question, want to contact me privately, I will stay here for a while. Okay, thank you.